Thank you, everybody, to be here for my presentation. So today, the first part of this presentation shows how vibroacoustic method is used as a fast diagnostic tool to easily detect mechanical problems in the tap changers, online or offline, before they create an outage. And the second part will present a real case showing how New Brunswick Power has used this tool to adjust properly an OLTC. So 40 to 50% of failures on transformers come from tap changers and are of mechanical origin. 4 studies done by Hydro-Québec, ESCOM, CEA, and Australia during 10 years on 3 continents, C-Gray, IEEE, show exactly the same results. You can see here in orange, 45%, like from the number from Hydro-Québec, and all the others, it's 33 to 35%. So what are the methods? Sorry, I got some. What are the existing methods for OLTC testing? So we have 5 diagnostic methods: the vibroacoustic, motor current, dynamic resistance, dissolved gas analysis, and the thermography. And 3 of them are Zensol are doing them. So if you notice here the OLTC type, you have the vacuum type, reactor type, and resistor type. You can see here on the left. And now here for the problems, you can see that like the problems detected: linkage gears, timing sequence, control relays, motor, brake, lubrication, contacts alignment, arcing, overheating, cocking, contact wear, transition. This table come from C-Gray 8234. And now if you take, for example, the overheating cocking, you can see that it's excellent for the dissolved gas analysis. But for the vibroacoustic, it's like low. Big why? It's because it's a silent problem. It's not noisy. So, but you in exchange, if you see the timing sequence, you can see that the vibroacoustic and the dynamic resistance are excellent. So what kind of benefits OLTC's vibroacoustic testing bring to electric utilities? We have noticed 14 benefits. First, applicable to any kind of tap changers. Applicable online or offline. Quick, easy, and intuitive test, similar to a stethoscope, because you listen something. With vibration and current combined, we are able to detect a large range of potential problems, as the previous tables has shown. But so better understanding of how the tap changer OLTC works. Why? Because we have some impacts and we are obliged to understand how this sound or how this noise is coming. So thanks to this understanding, we can detect problems at earlier stage. It's excellent in terms of timing and mechanical adjustment. It's an easy tool to detect arcing contact problems, of course, online only. We have a powerful software, and thanks to the Hydro-Québec, we can do like a simple analysis. The high sampling time, unlimited recording time, unique in the market. It's an excellent tool to help the user to decide which OLTCs are due for a maintenance operation. And in testing OLTC before and after maintenance, this tool also can be used for quality control. And in testing year after year, trending analysis becomes easy and allows reduction of maintenance interventions. And of course, our goal is to reduce the transformer failures. So typically, the transition of the diverter switch is done in only 50 milliseconds to avoid overheating the resistance. So we are able to listen all the impacts of the mechanism during a step up or step down operation. So here you can see in this graph the resistive OLTC type diverter switch operation sequence. And here we're going from doing a step up from tap 3 to tap 4. And here you have all the the seconds. And of course, if this the timing is long, so we are in trouble. If it's less, well, it's not so bad. The motor operates between 2 and 12 seconds. So the motor drive mechanism, this motor allows the tap changer to move from position to another, and in recording, analyzing the EC or DC current of this motor during the step up or step down operation, we are able to know if the mechanism are forcing or not. And also what is important for us, because the step up or step down is for our recording system, it's an event. So these events, we need to have the start of the event and the beginning of this event and the end of the event. And the current is perfect for this operation, because the motor current allows us also to start and stop the recording. So in fact, we have a window of this event. So what is the diagnostical principle of the vibroacoustic? Each operation of an OLTC produces a specific vibroacoustic wave pattern. We call this a signature or a fingerprint. And with a vibroacoustic sensor, which is an accelerometer, we can record this signal the same way a stethoscope picks up a person's heartbeat. And a stable OLTC always shows consistent signatures. Any degradation of the OLTC induces changes in the signature. So here on the left, you see a typical recording. Like in blue, you have the raw data, which is a vibroacoustic signal. And in red on the top of it, you have the envelope. And from this, we extract what we call the high frequency envelope in red and the low frequency in green. And on the bottom here, you have the current envelope. So now, why envelopes? Because it's simplified the signal, it gets the shape of the signal, we focus on valuable impacts only, it's easy to analyze, easy to compare. And thanks to impacts understanding, thanks to the envelope. So here it's typically this is our challenge, it's to understand these signals. In fact, thanks to the current, we call this the startup, we have a changeover switch, which is in general silent. The diverter switch here is operating. Here we have a contactor acting, selector switch silent. We have a new operation, a diverter switch operation. And then after, we have to analyze absolutely the breaking part of this event. So this is typically what we do. First of all, we record and we get raw data. And the raw data is typically this, like here we have an EC current, motor EC current. Here we have the vibroacoustic signal. And from this, we extract what we call the envelopes, the Hydro-Quebec envelopes. We get an Excel report. And then after, we can use these two tools, but what we need to do what we call an offsite deep analysis. And typically, a diagnosis can be made in 15 minutes for an online test and 1 hour for an offline test. For example, on on-site quick analysis, here you can see a current, which is, it has to be stable, it has to be flat, and it's not. So we can detect quickly a problem of the motor current. And for the offsite deep analysis, sometimes it takes minimum 3 hours could take 4 hours. Well, it depends of the problems, because we go through what we call the Excel reports. Thanks to this, we have the contact wear, we analyze the envelopes, we have diagnostic cards, and after we can do some comparison with the Zensol database OLTC references signatures. Here we have an example of wear of contacts. In Val-Tirfo, this is in Quebec, severe wear of contacts, here as you can see here. Before the intervention, more than 60% of difference between the high and low frequencies. Here you can see like the high frequency in red and low frequency in green. And here after the intervention, less than 20% of difference between the high and low frequencies. With the experience, with a lot of times you can use the analysis of low end frequency and low and high frequency envelopes. This is a really simple problem to detect. Here we have an unusual shape of the motor current envelope, which is foreseen, and it was a simply poor lubrication. Here also an example of asynchronism. Here you can see the impact has happens at the end of the current, 120 millisecond delay after the end of the current envelope. So this is not normal. This is before repair. So, and when the adjustment has been done, so now we have the exact transition at the right time. Here we have an example of arcing contact. Because the accelerometer has some quality, it can detect the arcing. And here we can see the comparison between online and offline test. Offline, it's in red. You got a value of 7G. And here on the offline, we get an amplitude of 35G. When we zoom this part, you can see that the arcing is happening exactly at this time. So with this information, after you can surely like guess that your contact has some holes and it's not in a good shape. Here it's an example of impacts and timing association. So here this is how this vacuum tap changer is operating, and with this information and the impact, so we can associate exactly how the transition happens. Here we have an example of abnormal inrush current. One comparison of the inrush between two transformers exactly the same type. This one is delayed. This inrush was not normal, so this it was a brand new tap changer with a transformer, but very not well adjusted. It was simply like a timing was not working properly. Here it's another abnormal forcing current that you can see. Here we have some examples of analysis. Like here you can see in red, the current was done in 2014, and it was like a step up between tap 16 to 17, and 2 years after, what kind of exactly for the same step up, you can see in 2016. So you have some differences, and here exactly the same, but it was for a step down from 17 to 16. And here it's not correct because the connections was not done properly. Here you have an analysis done in 2014, 2014, 2016, 2016, and here it's showing how the connections have been done. So this way you can analyze how your the trending of your motor current. And also here we have like a case of a break analysis. So it's important in our system of systematic analysis of what we have developed. So now the problem, for example, and I go quickly here on this, the example of impacts and timing association. In the past, it was really hard to analyze because we got motor current, we have impacts, so we need absolutely to do some guess what is this impact is coming from. And so here on this case, we need absolutely a very good knowledge of how the tap changer is working. But now with the, so it's why so now it's why we had, like in the past, a challenge. It's how to facilitate the comprehension of vibroacoustic signature. So because several mechanisms are operating at the same time. So one way to address this challenge is to analyze simultaneously 3 recordings: the vibration, the dynamic resistance, we call it the DRM, and the motor current of the tap changer in action. So here, what we need what we call a tap 4 plus that you see here on the bottom, a tap DRM on the top, and this is a kind of connections. And of course, this test is a test offline. So it's an example of a DRM recording, and here it's like a high-speed camera connected on EBB UZ ERN tap changer, and here you can see how it moves, and for each step we got some impact. So I can do it again. So here we are moving from tap 1 to tap 2, and here it's typically like a well-known curve for the dynamic resistance. And here it's what we get. We get the dynamic resistance, the vibration, the motor current, and when you do like a zoom of this part, you see exactly which the transition is going. Here you have exactly the same, but with the high-speed camera, and for each impact you have a transition happening. So these are examples of recording for different OLTC done with tap 4 plus and its accessory tap DRM. This is for an AMR and an EBB. And here it's an example of a recording done with the Hydro-Quebec, like in summer, tap DRM, tap 4, the current clamp. And here at this tag is here to show to the next one, to avoid the kind of problems that you have seen in the previous slide. So for the next test, it has to be done with this wire exactly, not another one, to get, so not lose time on the recording, on the setup. And here you have the accelerometer and the connections of the transformer, which is offline. So this is the checking. So now this is typically what we get, like this is raw data. So here you have the motor current, you have the vibration, the current, the voltage, and the calculus, the dynamic resistance, which is calculated here. So under here you can see the resistance transition, the voltage, current, and we are looking for a current drop because of a transition resistance. And here is the Vibro-Acoustic, and here you can check, so normal seconds after all verifications of timing and impact. And the next slide, because like the client was suspecting some wrong transition between tap 8 to 10 and 10 to 8. So here it's what we have done. It's like we have done a lot of tests between 8 to 10 and 10 to 8 that you can see here. So here you have the motor current, the accelerometer, so the Vibroacoustic, the voltage, the current, the voltage, and the dynamic resistance. And also you can do what you want, in fact. A special test done between tap 15 to 17 and 17 to 15. So when you suspect like some wrong functionality, so you can focus on this particular transitions. And look at the arrows showing that voltage or current are not interrupted at all. Here it's some impact analysis, so current, vibration, dynamic resistance, and here it's a zoom of the dynamic resistance. You see, you can, so after the association, the correlation between the impacts and the transition is easy. So with this fact, so when you do like an offline test, so you learn what is the vibroacoustic signal. So after, you just have to do your test online, and you just use the motor current and the vibroacoustic only, without the dynamic resistance. Because, and during this process, you have learned what is your vibroacoustic signals and what impact has is valuable. So this is what we recommend. It's an example of action plan to elaborate a predictive maintenance for transformers with OLTC. Step 1, establish your transformers list with OLTC to monitor. In general, we look for strategic transformers. Step 2, for each transformer, do a complete test to get a reference all taps offline, tap 4 plus tap DRM. So here we have developed a Zensol checklist. So this way you go through your inrush current, your vibroacoustic, and your transition, and your break part. Step 3, produce a complete report analysis for each transformer, OLTC, and here we have developed a Zensol report analysis. So, and if you're able to go to produce this report analysis, so after you know exactly, and this is guaranteed, that you know exactly how your tap changer is working. Because, and also you take a lot of informations, and based on the timing, how it works, what kind of operation you must get. So it's really a lot of good informations. And then after, step 4, according to the diagnostic results, so now you can establish your maintenance plan for each transformer. So first step is exactly to produce this report analysis, which is important. It takes some time to get this report, but it's really a great benefit. And step 5, after, you just have to do periodic vibroacoustic test online or offline. This is really what we recommend. So now I come to my second part. Randy, I have put 24 minutes. I'm sorry, but is it okay for me? I continue?
Yeah, sure. You can continue, sure.
Okay, so the second part has been done. It's like by an engineer, Christian Noel, who works for New Brunswick Power, and has presented this in SANCS 2023 in Fredericton. And here they have done maintenance in Caracat T1. It's LTC maintenance on an MR type vibroacoustic, and they are performed before and after maintenance. And this maintenance was performed on our Caracat T1 transformer. This transformer is equipped with a Renhausen type M3 500 tap changer. So here, for me, I'm just the presenter of its work. So here you have a picture of what they have done. In general, there are 2 types of LTC, compartment or box type, and in-tank design. In our case, this LTC is an in-tank design. Although most of our in-tank design LTCs are 3 separate phase models, we do have a few delta configuration. A delta configuration has a cylinder with 2 diverters, and the other is a regular cylinder with a single diverter, as you can see here in this picture. So the W is here, is connected, and the U is alone. So timing between the motor drives and diverter assemblies is adjusted using the shaft connections between them. So here you have a view on the top of these 2 tap changers. So vibroacoustic sensor locations. In this case, we install 2 vibroacoustic sensors, 2 on separate walls near the diverters and located about 8 inches from the cover. In fact, we recommend only 1, but when you are not sure, it's good to do like 1 or 2, maybe 3, because the instrument allows it. And then this way you can choose which location is the best, but after it's important to keep always the same location for future test. So generally a tap operation on this style of tap changer will include the following steps. One of the selector contact is leaving the previous type position, stationary contact. This moving selector contact is then connecting to the next tap stationary contact, and the energy in the diverter energy accumulator is released to switch the load current to the next tap connection. On this graph, we are seeing the sound made by each operations being captured by both vibroacoustic sensors and also the MDU motor current captured by the EC clamp on CT. As I told you, you can see here the first accelerometer, and the second gives exactly the same information. So when adding the DRM information to the previous graph, we can then confirm when exactly the diverters are switching the current. It helps understand the information provided by the vibroacoustic sensors. So here, for example, you can see that the transition happens exactly here, not here. So here, this is a tap up operation before maintenance. The results shown are from before the maintenance. You're seeing all 3 phases side by side. From this information, we can tell that A phase is not operating in synchronization with B and C phases. A phase is likely the single diverter, where B and C phases are associated with double diverter cylinder. Here you can see like A phase, you see the impact is coming when you see the end of the current. You see it's coming here. Look at the end of the current. And for B and C, it comes here. So in fact, it's clear that it's not adjusted properly. So our test plan calls for testing all the tap transition going up and also back down. In this up operation, we're seeing that A phase is operating early than B and C. But in the down operation, we are not only seeing that A phase is operating slightly later than the other 2 phases. In fact, A phase is operating after the motor current is interrupted. So the timing of this diverter is at the limit where it could possibly not operating during the down operation. This would result in a phase being on a different tap than the other 2 phases. So now, and then the graph is now showing the acoustic signatures and DRM information recorded after our maintenance. We're seeing A phase operating now around the same time as B and C phase originally, which was 4.25 seconds. So, but the big improvement can be seen on the down operation, where A phase is operating well within the runtime of the motor now, and this aligns with what was seen for B and C phases. So, like here, just to review the before maintenance reading, showing the difference in timing between A phase and the other 2 phases. So, as we have seen here, so this is before maintenance. And now it's after maintenance. The after maintenance results now indicate the timing between all three phases is now better adjusted. The selectors and diverter operations are now more in synchronization. I'm not showing the down operation, but the timing was the same as the up operation shown on this side. So here you can see the good adjustment, you see, exactly at the same time for E, B, and C. And summary, Zensol Tab 4 can give a good indication of the timing between diverters. When time allows, it can be used before and after maintenance to validate the LTC is operating properly after our intervention. And as we're getting more experience with the information provided by the Tab 4, we could use offline acoustic measurement to focus, prioritize maintenance on the specific units. That's it.
Okay, if you have any questions for Fouad, please type them into the chat and I will relay them to him. Fouad, you mentioned in the beginning of the presentation that 40 to 50% of transformer failures are from tap changer failures. Is that in older transformers? What's the average age of a transformer failure related to tap changers? Can it happen at any age, or is that the older transformers?
Well, it's a good question. So in my point of view, well, I can check in this in the study, but I think it was on in general, it's for all transformers. Really, I think I need to read a little more.
Okay.
The study and then
what I was
just yeah.
what I was getting at was whether or not this is an investment that transformer owners need to make for the life of their transformer from the very beginning, or is it suitable for transformers at an older age?
Yeah. Well, so this is another I think you have opened like a new field of exploration, because
wow.
yeah, no, seriously, but I
like
don't
when
know.
it comes to oil monitoring, they suggest oil monitoring right from the beginning of the life of the transformer.
Mm-hmm.
But really the failures, mostly take place in older transformers.
Yeah, well,
more than 10 years
this
old.
Yeah, but well, this is what I think, but I think it's a good question, because me personally, I would like to check in the study if they give an information about the age of the transformer. Do you understand what I mean?
Yeah, I understand.
Because when you do like a study, you just take a transformer, but I think it's another parameter of study. This is what I think.
Okay, here's a question. Are there guidelines or recommendations available regarding the expenses associated with an online system encompassing hardware, software, and installation costs?
Can you repeat?
Are there guidelines or recommendations in the industry available regarding the expenses associated with an online system, which encompass hardware, software, and installation? Are there guidelines for this kind of technology?
On my best knowledge, I don't know.
All right.
But what I can say on my knowledge, like on the if no, you are talking about online. So on online, I cannot I cannot answer.
Okay.
I think I don't know. I need to
I put into the chat, Claudio, your Fouad's email address. You can ask him.
Yes, I would
Afterward.
like, because I think it's these when the problem is when I don't know the answer, I prefer to say I don't know, and then take some time to get the answer and send it on my best knowledge.
All right, that's great. I've also given everyone the presentation that you just made. Everybody our presenters asked me to make the PDF available after the presentation, so that's why I've given it to you then. And there's Fouad's email address, so you can all contact him directly if you have questions regarding his presentation.